Alright, so 3.1 we're going to look at graphing and just overall just, what are the different graphs, how do we graph different graphs and so forth and so on. But the main thing I want everyone to understand about this section is that it really comes down to your graphing calculator. It's time for you to, if you don't have one, to make sure you have it and to be utilizing it and practicing it as we move through. So first thing is that I want to run through this slide right here, and these are very important for you to have a visualization of the different types of graphs we're going to deal with. The only one on the screen that we're not going to talk about necessarily right now is going to be the reciprocal. I left it on this slide only because we do talk about it later, so I figured at least we can have it in place and we can kind of see, oh, that's the reciprocal. So we're going to look at specific examples of these in this first video, but more importantly, I just want you to understand is that these are what's called the parent function. So everything we're going to talk about today is going to revolve around these guys right here. So please hit pause, draw a sketch of each one of these, take the name down, so go ahead and draw yourself a rough sketch. Write down that the equation. So remember that y, or that's f of x equals a. That could also be said as y equals a. Just like this would be y equals x, and this would be y equals x squared, and so forth and so on. The f of x and y are synonymous. It's called a constant, called a linear, called a quadratic, called a cubic, square root, cube root, absolute value, reciprocal. Okay, once again, these are the parent functions. So what I mean by parent functions is that we're going to be able to identify characteristics of graphs based upon the different transformations and where the transformation is inside of the actual equation. So this box right here is very important, so you want to jot this down in your notes right here. Okay, I had this color coded based upon its location inside of the equation. So a quadratic has this foundation question or foundation equation where the a will always fall into place, where the h falls into place, and where the k falls into place. We know that if we have an a value that is negative, so for example, if I had an equation like y is equal to negative 2x squared, that graph right there would be a reflection over the x-axis from the parent function. So that would be a graph like something like, oops, my mistake. It would still start at 0, 0. But don't get caught up in the graphs right now. I'm just kind of going through the rough idea. Like for example, if I took and I said, okay, my a value is a fraction, so it would be like 1/2. Oops, I don't need that. X squared. Then that means that I would have a vertical shrink, which basically means that from the parent function, my graph would just grow more slowly. Or in this case here, we kind of had a similar situation with the first one, but if we did y equals 2x squared, so my a value is greater than or equal to 1, in that case there I'd have a vertical stretch, which basically means that my graph would grow more quickly. And I'm just writing down some generic words like slowly, quickly, so that you can have that relationship there. And then from there we can add other things on, like we can add the h value. The h value moves me side to side. We got the k value. The k value moves me up and down. And when I say it moves me, I'm talking about basically considering that vertex right there. It moves every point. So like, on this first graph we have the point 1, 1. So when you move it, it would move that point over 1 or up 1 or over 2 or however the transformation was. But the vertex is kind of a safe spot to go from. Alright, the cubic function has a similar equation. You see the format is exactly the same. Got the a out in front, the h is on the inside except it's cubed instead of squared. And then you have your k. Kind of just running through. Square root, same deal, has the same type of function, just has a square root around it. Cube root, same deal. Absolute value, same deal. So this is the one slide right here that kind of has a sketch of each one of the functions and its adjustable equation, however you want to call it. It's equation that has the locations for the transformations for each of our parent functions that we're going to discuss. So this is a great screen right here to have all in one spot. It's going to be a huge resource. So hit pause, copy down what you need, keep it organized and neat, and then hit play again and pick up where we left off. So we take a look at this guy right here, and these are 4 or 5 examples for us to look at and talk about what type of transformation. So when we look at this first one, what we see is that we have y is equal to, there's no a value, there's no number out in front, but we have x, and I'm going to color code it based upon the actual variable. So I'm going to rewrite it as a color coding. So you can see that that 6 is my h value. Alright, and what I mean by that it's opposite is that if you think about on a number line, you think 0 is right here. If this says -6, let me do that differently. If this says -6 right here, we're going to go opposite. So since negatives are to the left, we're actually going to go to the right over 6 times to the right, and we'll be out here. So this guy right here, the first one, letter A, would be a shift to the right, a translation to the right, 6 units to the right. So that'd be letter E. And where are we going to put that? Let's put it right here. Because that's a shift. That guy moves me. The negative is opposite, so it moves me 6 times. I go to the next one. We can think about this as y equal an x squared. And let me modify color real quick. Get some yellow. And so we get x squared minus 6. So notice the minus 6 is not inside the parentheses. The minus 6 is on the back. That means it's my k value. And so that is direct correlation that that's a vertical shift, and minus 6 tells me that it's a vertical shift going down 6 times. So let's see, a translation down 6 units. There we go, so letter D. We go to letter C. On letter C, we have y is equal to, and remember I'm color coding this so that you can kind of see where you're pinpointing in on. So that means that this 6 is my a value. So I come up here and I say, okay, my a value, which is on the front, if my a is less than 0, a negative number, I'll reflect over the x-axis. If my a is between 0 and 1, then I'm a fraction. That means I'm a fraction. That means I'd have a vertical shrink. If my a value is greater than 1, and really that equal to sign should not be there, I apologize. If it's greater than 1, that would be a vertical stretch. So this 6 right here would create a vertical stretch. So the correct answer for this guy would be C. Letter D, we have y is equal to x, oops, let me back up and do that coloring right, x plus 6 quantity squared. So that means that that 6 right there is my k value. Positive 6 is actually to the right hand side, but we're going to do the opposite, so it'll be negative 6. So this guy would be a translation 6 units to the left, which would be letter B, because it's opposite of what's inside here. Last but not least, very similar to one previously, is that this would be y is equal to x squared plus 6, so that's my k value, and so this guy would be a translation up 6 times. And so that would be letter A. So that's the main gist of this section is being able to go through and just identify the transformations based upon what you see inside compared to either this equation or the radical equation or the cube root equation or the absolute value equation. But any of these equations come off of these commands or these directions right here. All right, let me hit pause real quick and make sure that wraps up this video. So the next part to this is that I have a series of practice problems, and so what I'm going to do is I'm just going to record a separate video for that. That way we can kind of close this video off. Here's the instructions of how you do it, and then I'll have a video where you're just practicing the problems similar, and so you can make a separation between the 2 videos. Alright, so this closes out this idea of looking at parent graphs and comparing the parent graphs to their transformations of their new graphs.